So for today, let us have the solution suggested by the equation, or it is also known as the obvious substitution. So from the word obvious, it should be obvious to you which term or terms of the given differential equation will be introduced to a new variable. A possible solution of a differential equation is by doing chains of variables to transform the equation into a type which we know how to solve. So what if after evaluating the given differential equation, it is any or none of the uh, forms or methods that we discussed earlier? Then how are you going to provide the solution of that differential equation? So a possible solution, as mentioned, is by changing a variable to transform into equation in which it will fall to any of the form or methods that we discuss. A natural source of suggestions for useful transformation is the differential equation itself. If a particular term or terms stand out in the equation, it is worthwhile to take time to study the equation after the term has been introduced as a new variable. So to illustrate you the process of obvious substitution or the solution suggested by the equation, let me give you the following sample problems. The first problem, we are asked to solve the equation, the quantity 3 tangent x minus 2 cosine y secant squared x dx plus tangent x times sine y dy is equal to 0. So as you notice here, looking at the terms of the differential equation, you have tangent x, cosine y, secant squared x, tangent x, and sine y. We have tangent x and it is related to secant squared x dx in a manner that the derivative of tangent is secant squared x. Or maybe we can also try cosine y and its derivative is sine y dy. There are times in a given differential equation you can do actually more than one obvious substitution, but you will end up with the same solution. So to illustrate the method, let me use this tangent x and this secant squared x. So if I let u to be equal to tangent x, then our du is secant squared x dx. So we will be replacing all tangent x by u and the secant squared x dx by du. So continuing, this is now 3u minus 2 cosine y times du plus, that is u times sine y dy is equal to 0. Okay? And now, what are we going to have with this differential equation? What is then the differential equation formed? If you are going to look here, this is not a separable equation. Can you separate u from y? Or is it homogeneous? This is not homogeneous. Is this linear? You have here y dy and you have u du, so it is not linear. Is it exact? Then maybe we can test for the exactness. This is now your m du plus n dy is equal to 0. So this is our m. So the partial derivative of m with respect to y, so we differentiate negative 2 cosine y, so that is 2 sine y. And the partial derivative of n with respect to u is equal to sine y. Looking at this, they are not equal, therefore it is a non-exact dE. But maybe we can find an integrating factor to make it exact. Okay? So let us see. if we can make it exact. So taking the difference of the two partial derivative, you have here 2 sine y minus sine y, that is sine y. So comparing it to our m and to our n, we divide it by n. So divided by u sine y. And therefore you have 1 over u. So this is a function of u. So therefore our IF is equal to e to the integral of 1 over u du, or simply e to the ln of u, or u. Okay? Then, that integrating factor, if we multiply it to our m, so that would be multiplying it, that is 3u squared minus 2u cosine of y dy du plus u squared sine y dy is equal to 0. And this is now our new m. So taking the partial derivative of m with respect to y, that is negative 2u times the derivative of cosine y, so that is 2u sine y. And the partial derivative of n with respect to u is sine y times the derivative of u squared, which is 2u sine y. And now they are equal. Therefore, we made the given differential equation exact with the integrating factor of u. And so we continue solving for the function of x, this is u. U and y is equal to c. Let me use m. So we integrate with respect to u. So f is equal to the integral, this is our new m, of 3u squared minus 2u cosine of y du. So integrating, the integral of 3u squared du is 3u cubed over 3. So that is u cubed. Then you have minus 2 cosine y. The integral of u du is u squared over 2. So you have minus u squared cosine of y plus the constant of integration, p, as a function of y. Then we differentiate with respect to y. The partial derivative of f with respect to y would be equal to negative u squared times the derivative of cosine y is sine y, negative sine y times this negative, so it will make it positive. So that is u squared sine y plus t prime of y. But again, the partial derivative of f with respect to y is equal to m. So you have u squared is equal to n, u squared sine y is equal to u squared sine y plus t prime of y. So therefore, your t prime of y is equal to 0, and integrating, you have t of y is equal to c. Therefore, substituting it here, you have u cubed minus u squared cosine y plus y is equal to c is equal to c. Okay? But what is u? But u, initially, we assigned it to tangent x. Therefore, substituting it here, you have tangent cube x is equal to c plus tangent squared x cosine of y. And that is now the solution of that differential equation, in which obviously we use tangent, introduce it to a new variable, and its derivative is secant squared x dx. Okay, so that is the first example for obvious substitution. Now we go to the next sample problem. Solve the derivative of y with respect to x is equal to 1 plus 6x times e to the x minus y. So again, if you are going to inspect this or to determine the form of this DE, you cannot identify a form of DE for you to provide a solution. And therefore, let us try if we can solve it by obvious substitution. What could be obvious to us here? You have derivative of y with respect to x. You have x and then e to the x minus y. So with this example problem, let us have this x minus y to be introduced to u. So we let u to be equal to x minus y. What is therefore our du? This is dx minus dy. Sorry. So you can actually find your dy here would be equal to what? So dy is equal to dx minus du. Then we replace dy of our given dE and the x minus y by u. So you have dx minus du. Dx is equal to 1 plus 6x e to the u. Okay? And then simplifying the equation, you have dx minus du is equal to dx plus 6x e to the u dx. So dx minus dx. And therefore, you now have negative du is equal to 6x e to the u dx. And now, how can we solve now this differential equation? What is the form now of the resulting equation? You have here du, but on the right side, you have x dx, and you have e to the u. So we do not need here your e to the u. And therefore, by separation of variables, we can separate them if we divide it by e to the u. So therefore, you have negative e to the negative u du is equal to 6x dx. Okay? So integrating both sides, what is the negative integral of e to the negative u? That is e to the negative u is equal to 6x squared over 2. So that is 3x squared plus c. Okay? And then, but what is u? U is x minus y. So substituting it here, e to the negative x minus y is equal to 3x squared plus c. Or simply e to the y minus x is equal to 3x squared plus c. And that is now the solution of this differential equation, in which it resulted to a separable equation. So as you can see here, the solution of the problem is not similar to what we had in some of the forms of DE, in which we follow certain procedure to provide the solution. The solution for method by obvious substitution actually depends on the given terms of the differential equation and also on your ability to recognize or to determine which term or terms of that DE will be introduced to a new variable.